Yes, good day viewers. This is 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next exams. Of course, this is about time for volumetric analysis, otherwise called quantitative analysis, final revision. Um, Looking at feedback from the last video lecture on volumetric analysis for this year's Waec examination. We've decided to quickly, look at some of the tweak and some of the gray areas and some of the, changes and the twists and turns that may want to occur in the course of the exams, and as well looking at the calculations. What are the adjustments that can happen so that we are better prepared to tackle things. Like we already know, the titration this year is not the conventional acid-based titration. It is a redox titration between purple potassium permanganate, or you call it potassium tetrahydromanganate 7, and iron 2 tetrahydrosulfate 6. The potassium permanganate, deep purple in color, goes into the burette that is tagged our A, and of course the iron sulfate is going to be in a cylinder, so to speak, from where we are going to pipette a definite volume of the base into a conical flask, of course, before we run our KMNO4 or before we titrate our KMNO4. And in this case, for this redox titration, we know our endpoint by, we dictate our endpoint via color change. Now, the color of the KMNO4 here is purple. Actually, as you can see on your screen, the KMNO4 is deep purple. But the thing is this: in the course of titrating against iron sulfate here, as soon as the KMNO4 get in touch with the iron sulfate, the deep purple color disappear. Once you swirl around, once you mix together, the purple color and everything here turns colorless, and that is going to continue until a point is reached where some few drops is just not going to turn colorless even when you swirl and mix the whole mixture together. No, it will not remain colorless, but rather at the end point, the color of the mixture here is going to change from colorless to light pink. So invariably what we say here is that the purple color of the potassium permanganate at the endpoint changes to pink. That was why we talked about the results here. Purple color of potassium permanganate changes to colorless. First in FeSO4 it changes, then at the end point it reappears as light pink color. So that is the result. So do we need an indicator here? No, we don't need an indicator, because KMNO4 on its own is a self indicator, given that it is a very strong oxidizing agent. What are the procedures we are going to follow for this titration? We're going to pipette 25 cm cube or 20 cm cube, depending on the type of pipette you have in your school. We're going to pipette a known volume of the base into a conical flask. Yes, someone did actually comment that we are going to need sulfuric acid for this experiment, that we have to acidify our potassium permanganate using H2SO4. And I did reply in the comment then that, look, in preparing your KMNO4, it is very, very possible that your instructor or your teacher must have laced the KMNO4 with sulfuric acid. But looking at what question usually looks like when in this redox reaction, so the procedure is that you pipette a known volume of iron sulfate. After the pipetting, before you run in your KMNO4, you must add your H2SO4. Why are we acidifying? I'm going to talk about shortly after now. So pipette your iron sulfate. Pipette your iron sulfate into the conical flask. Add 25 cm cube of H2SO4, or just about any meals you're told to add on the day of your exam. It will be in the Waec question. It's going to be clearly stated if you are adding any thing. If it is 10 meals or 10 cm cube you're told to add, just measure exactly that and add to your iron sulfate to acidify the whole setup. So the procedure is pipette, and then you acidify, and then after that you titrate. Pipette, acidify, then you titrate depending on the instruction you're given. So the big question now is, why are we acidifying? I'm going to talk about that now. So talking about the reasons why we are acidifying, top on the list is the fact that KMNO4 is quite expensive. So we say for economical reason, that is what is behind every other reasons. And the way it works here is this. You see, when we have the equation in itself, what we have is MnO4 minus plus 5Fe2 plus 8H plus to give us Mn2 plus 5Fe3 plus 4H2O. So when we look at this, normally if you calculate the oxidation state of manganese here, it is +7. So you're looking at from +7 to +2 here. So what that means is that we expect this manganese, you know, from +7 to +2, reduction in oxidation number, that is reduction. What we undergo reduction, oxidizing agent. So our potassium permanganate is the oxidizing agent here, from +2 to +3. That's an increase in oxidation number. So in this case, we're sort of expecting iron 2 ion to even give out electron. Giving out the electron to who? It is to give out the electron to manganese. So that manganese that had lost 7 now, it appears as though it has lost 2. Here is gain of electron, here is loss of electron. So what is happening from iron 2 ion to iron 3 ion here is actually oxidation. And what we undergo oxidation is actually the reducing agent. So let's assume a case where the iron has been left exposed to air. What that means is that even before the titration here will happen, most of the iron would have lost their electron to oxygen in air. And by the time we are now titrating, so what that means is that when we are now titrating and tetrazomanganate ion gets into the solution, of course, most of the electron iron 2 ion is supposed to give out had already been taken up by oxygen. The implication of that is going to mean that we will now have to run so much of the purple permanganate before we can get a color change. So the thing is this: when we acidify a solution, we are acidifying a solution so that the iron 2 ion is preserved, and not that most of the iron 2 ion had been converted to iron 3 ion, so that by the time we then run our tetrazomanganate ion, it is going to be very easy for manganese tetrazomanganate ion to oxidize the reducing agent. This here is our reducing agent here. Reducing agent wants to give out electrons so that manganese will now collect or accept that electron to become manganese 2 plus. So we are basically acidifying to prevent, you know, oxidation of iron 2 ion to iron 3 ion, or you say so that tetraozomanganate ion can easily oxidize the reducing agent. That way we are going to use less amount of KMNO4, because the moment we titrate, it now means iron 2 ion will be available to donate or to give out electron to the manganese here. But if most of the ion had actually oxidized and changed from Fe2 plus to Fe3 plus before the actual titration starts, then it now means that manganese, tetrazomanganate ion, which is +7 here, to get 5 electrons to become +2 here, that's going to be difficult, in which case most of the manganese, tetrazomanganate ion will be converted into manganese 4 oxide. Here it is +7, here this is +4. So which means we're not going to get enough electron for tetrazomanganate ion here to become +2, because why? Most of the iron 2 ion are giving out the electron to oxygen. So simply, why are we acidifying? It is to prevent iron 2 ion from becoming iron 3 ion. It is to prevent iron 2 ion from becoming iron 3 ion before the actual titration starts. That way, the amount of KMnO4 we are going to use before we get our endpoint, we get a color change, is going to be very minimal, because when the KMnO4 comes here, there is more than enough iron 2 ion that will give out electron, and that will be oxidized. So that is the reason. It is to prevent oxidation of iron 2 ion to iron 3 ion. The next thing we're going to have to construct is our titration table, as you'd see in the question. Don't forget the procedure. You pipette your iron sulfate, you put in your conical flask, you add a certain mole of H2SO4, if it is 10, if it is 20, if it's 25, as CM cube you see in the instruction on the day of the exam. You add your H2SO4, that is to acidify the solution. And since the solution has been acidified now, it means we're not going to use much KMnO4, as the reaction will go to completion on time, given that KMnO4 is a strong oxidizing agent, and more so, iron 2 ion has been prevented from being oxidized into iron 3 ion before the actual titration. So in constructing our table here, talking about our titration table, the first thing we're going to have is the rough. Okay, we are starting from 0.00 here based on experiment performed already. Initial is at 0.00. This exactly here stops at 18.30. So it's like you started running your KMnO4 from 0. When it goes to 18.30, the color change from purple to a light pink. So this minus this, that's 18.30 minus 0.00. That gives us volume of KMnO4 used is 18.30. So if after we've dealt with that, for our first titration, we continue from that 18.30. So we say our initial burette reading is 18.30, and in that particular experiment, this stopped at 36.30. So at 36.30, the difference between this and this 36.30, that gives us 18.00, after which we then had to fill up the burette again, getting back to 0.00, and this time around we use the 18.20. It stopped at 18.20, so to speak. So from here to 18.20, we got 18.20 for our second titration, talking about the volume of KMnO4 used. So given that the KMnO4 on the day of the exam, might not be enough, and all of that, putting that into consideration, you may just stop at the second titration, or better still, after your rough titration, you should be able to formulate your table. So this is just rough titration. So as you can see in the question on your screen, the first thing we were told to do is to look for the volume, average volume of KMnO4 used. KMnO4 is our A, don't forget that. FeSO4 is our B. So the average here, if you look at this, 18.00 and 18.20, that is consistent enough. We are looking at plus or minus 0.50 from the endpoint of your instructor at your respective school. So this is going to be 18.00 plus 18.20 divided by 2, and the average volume of KMnO4 used in that regard is going to be 18.10 cm cube. Of course, if you missed out on the last lecture, you can check the description of this lecture video. The link to the last lecture on volumetric analysis talking about redox titration is there. Okay, looking at the question you have on your screen, there is a bit of a twist to this. In this case, in the last lecture, you know, we were not given anything about A. We were not given anything about A, but for B, we were supplied information about B. So in this case, we were actually told to look for CA while we know CB. CB was our standard solution, but for CA, it was not standard. So we thought, okay, in what format could the question come? We could have it the same way we had it in the last lecture, and at the same time there might be some one or two twists to that, whereby in this case, let's say we were given the concentration of our KMnO4, and what we are having to deal with is looking for the concentration of our iron sulfate. That is what this question is about. So looking at the question, it says is the solution of 1.58 is a solution of 1.58 gram per dm cube. Yes, we were given a direct mass concentration for A there of potassium permanganate. Or better still, they might put it this way: 0.79 gram KMnO4 in 500 cm cube of the solution. That's what A is. And in the question here, we were not given anything about B. We were only told B is a solution of iron 2 tetraoxosulfate 6. So that's the information we have. So now, looking at this, we were told to look for concentration of B in mole per dm cube straight up. So we were told to look for the concentration of B in mole per dm cube. Take note that average volume of our KMnO4 of A used is 18.10 cm cube. So as you can see on your screen, the first question wants us to calculate the concentration of B, that's iron sulfate, which we were not supplied any information about, which means iron sulfate here is not standard, but for A it is standard, in that we have information about that. We have information about the concentration. So when you tell us to calculate concentration of B, the normal thing we are used to is to say, okay, CB, what is our VB? Our VB is 25 cm cube, talking about the volume of the pipette, and then our NB from the equation. Okay, let me put the equation here: MnO4 minus plus 5Fe 2 plus 8H plus to give us Mn2 plus 5Fe 3 plus 4H2. Of course, you must have been given this equation in the question. Here, Na is 1, Nb, this is our B, iron sulfate, is 5. So Nb here is 5. So for me to be able to unlock concentration of B in mole per dm cube, I'm going to need my Ca. I'm going to need the concentration of my Ca from the concentration of my Ca in mole per dm cube from this particular figure I'm given. So Va is the average volume of A used, that's 18.10 cm cube, and then Na in this regard is 1. Of course, I am looking for Cb. Even my Ca, I don't know what my Ca is, so it's only logical that first of all I have to look for a way to get my Ca. Now I'm looking for concentration of A in mole per dm. Concentration of A in mole per dm cube is actually concentration in gram per dm cube divided by the molecular mass. So if we are talking about, if we are given something like this, that's going to be 1.58 gram per dm cube divided by FeSO4. At the end of the question, we were given the molar mass as 158, so divided by 158. In that case, Ca in mole per dm cube is going to be 0.01 mole per dm cube. That is, if we are talking about, if we were given 1.58 gram per dm cube KMnO4. But if we were given information about KMnO4 as 0.79 gram of KMnO4 in 500 cm cube, how are we going to calculate our Ca in mole per dm cube? It's still the same process. Concentration in mole per dm cube is actually in mole per dm cube is actually amounting mole over molar mass. Amounting mole over volume in dm cube. Concentration in mole per dm cube is amounting mole over volume in dm cube. So mole here is mass over molar mass. Since our volume is in cm cube here, mole equals to mass over molar mass. That's for the numerator. And then the volume here, we have to change the 500 cm cube to dm cube. So what this means is that concentration of A equals to 0.79 as given in the question, divided by KMnO4 the molar mass as given is 158 from the question, 158, all divided by 500. To convert from cm cube to dm cube, you divide by 1000. So what this means is that my Ca is 0.79 divided by 1.58 times 100 times 1000 over 500. So from this, my Ca is also going to end up as 0.01 mole per dm cube. So irrespective of the information we are given about the acid, we should be able to get our Ca to be 0.01 mole per dm cube. So I haven't done that to get our Ca. We can then come here, the usual formula is to say Ca Va over Cb Vb equals to Na over Nb. Since we are looking for Cb, we're making Cb the subject. In making Cb the subject here, what this means is that Cb equals to Ca Va over times Nb divided by Vb Na. That is what this means. So that my Cb, what is my Ca, is 0.01 times Va here is the average volume of acid used, 18.10, times Nb, number of moles of base, is 5, all divided by, what is the volume of base? That's the volume of the pipette, 25 times 1. We are going to get 0.036 mole per dm cube. So that way, if you look at your screen, we've been able to answer the first question correctly. Concentration of B in mole per dm cube. Now, to the second question. This is Roman figure 1. This is Roman figure 2. To the second question, they wanted us to calculate concentration in gram per dm. Concentration in gram per dm cube is actually concentration in mole per dm cube times molar mass, and in this case that is actually 0.036, because we're looking at concentration of B in gram per dm. 0.036 mole per dm cube times what is the molar mass of B? B is iron sulfate, and that is 152. That is 5.47. That is 5.47 gram per dm cube in this case. 5.47 gram per dm cube. We've been able to calculate Roman figure 1 and Roman figure 2, and indirectly we were not told to calculate Ca, but if you don't calculate concentration of A in mole per dm cube, but what we have here is in gram per dm cube. If you don't calculate it in mole per dm cube, then you will not be able to actually deal with this. Remember that in this particular question, we were given Ca. So Cb is not a standard solution. We are looking for Cb. We're dealing with Cb, and that's exactly what we have done. So moving on, we were told to, for question Roman figure B3, we were told to calculate the number of mole of iron 2 ion in the volume of B pipetted. What is the volume of B pipetted? Volume of B pipetted is actually 25 cm cube. So we're looking for the number of mole of iron 2 ion. Number of mole of iron 2 ion, that is number of mole of iron 2 ion that is inside 25 cm cube of FeSO4 pipetted. Okay, this is a very simple thing. There is nothing I can do here, but since I now know I am dealing with B, which is my iron sulfate, I'm dealing with B. This is B3. Since I'm dealing with B, talking about iron, sulfate, then I have to make use of the concentration of that B in mole per dm cube. The 0.036 mole per dm cube here means that we have 0.036 mole of iron 2 ion inside 1 dm cube. 1 dm cube means 1000 cm cube. So what this means is that we have 0.036 mole of Fe2 plus in 1 dm cube, which is 1000 cm cube. So knowing fully well there is this formula, N1 over V1 equals to N2 over V2. So in this case, this is going to be NFE2 plus equals to, what is the V1? The V1 is 25, N2 is 0.036 divided by 1000 cm cube. This is in mole, this is in cm cube. So that what this means is that number of mole of iron 2 ion in the 25 cm cube is 25 cm cube times 0.036 mole divided by 1000 cm cube. This off. We're going to get 0.0009 mole, and that's justified if in 1000 cm cube I have 0.036, then in 25 cm cube I'm going to have way less than that. So that ends question 3. Looking at question 4, it says number of moles of KMnO4 present in the average volume of KMnO4 used in 1. Of course, this is similar to question 3. Question 4, we are looking for the number of moles of KMnO4 in the average volume of KMnO4 used in this reaction. The average volume of A as used here is actually 18.10. So we're looking at what is the number of moles of KMnO4 in 18.10 cm cube. When we know that the concentration of KMnO4 is 0.036 0.01 mole per day. So you have 0.01 mole of KMnO4 in 1000 cm cube. So number of moles of KMnO4 following the same formula, that would be 0.01 mole times 18.10 divided by 1000. That is going to give us 0.00018. Yes, 0.00018 mole, and that's justified. If we have only 0.01 mole in 1000 cm, then in just 18.10 cm we should have way less, and that is just that about that. Don't forget the calculation we took last class. The link to that lecture video is in the description, and that one we were looking for CA. In this case, we were given A, we have to deal with B, and with that we have come to the end of this series on everything chemistry practical for Waec 2024. When it comes to your question in the exam hall, I can tell you categorically that for all of the practical sections we've had, from volumetric analysis to salt analysis, the question you're going to see in your exam is 80 to 90% guaranteed. And with that, we've come to the end. Do not forget, subscribe, share with your peers. We appreciate those of you that have subscribed, but for most of us enjoying these lectures and are yet to subscribe, it doesn't take anything from you. Please do ensure to subscribe and share with your peers. From myself and the entire team, we wish you all the best in your chemistry alternative to practical exam, and as well as your Waec in totality. From myself, it's bye for now. Thank you.